This picture is kind of appropriate for the upcoming chapter we're going to be working on, which is oceans and climate change. We just finished currents, and they sort of tie in together perfectly. Currents control climate in many ways. So let's get started. The Earth's climate system needs you to first define climate. So climate, here's the definition from the book, The Long-Term Atmospheric Conditions in a Region. Kids frequently get climate and weather confused. So weather is what you experience on a day-to-day basis. So whenever anybody's like, oh, it's warm and it must be climate change, or oh, it's cold, there must be no climate change, a single data point does not prove a trend. So individual weather moments don't confer a pattern. So there's sort of this analogy that I like that helps define climate and weather in my head nicely for me. The weather defines what you wear on a Monday or a Wednesday or a Tuesday or whatever. The climate defines which clothes you buy. So, you may wear short sleeves today or tomorrow because it's been nice out, but you still probably own a winter jacket because you live in a temperate region, even if it's pretty warm in March. So that's the difference between climate and weather. The Earth's climate, we're going to talk about all 5 of these spheres to some extent or another. Obviously, we're going to focus on some of them more than others, but these are the interaction zones, and there's a lot of overlap between them. We'll talk about each one individually, but atmosphere, hydrosphere, geosphere. The biosphere is way more important than you probably have thought of before, and cryosphere is the ice system. And the climate system is just the exchanges of energy and moisture and the associated effects between all of those spheres. This picture is in the book. It's a picture where they're trying really hard to show you some of those interactions. It is both overly simplistic and occasionally wrong, but generally some of these are fine. So like changes in solar inputs, we're going to talk about that a little bit, but there's some of the interaction ones here. Let me circle some of them. This was an example of an interaction between 2 systems. The atmosphere interacts with the ice interacts with the hydrosphere interacts with the atmosphere. All of these are interactions that need to be taken into account when modeling climate, which you guys are actually going to do. Biosphere, atmosphere. This actually refers to that primary productivity thing you learned way back in freshman year, where the primary producers take up sunlight and carbon dioxide and turn it into sugars. Same thing in here and in here. So we'll talk more about these. People tend to focus on this one all the time when talking about climate. We will talk about that, human influence, and we will also talk about all these other natural effects. It needs to be said, this is obviously science class, and this is a science topic. As such, we're coming at it from that. We can talk about it more in class, but climate science is a science, and there isn't a lot of room for feelings in it. So try to keep your feelings out of the science as much as possible. This is a picture of a diagram, rather, of the atmosphere, and I don't actually need you to memorize them. I do need you to know that we live in the troposphere because we're going to talk about that. That's this one down here. Thanks, troposphere. Troposphere is the one closest to the Earth. It's also the narrowest one. And what I want you to see here is that the atmosphere is layered partly based on its composition, but partly based on its temperature. And there's sort of a zigzag thing going on. This is hotter that way and colder that way. The atmosphere up at its highest reaches is very warm. This is because of all the incoming heat from the sun, and there are particles in every level of the atmosphere in varying concentrations that will absorb light and radiate as heat. So the thermosphere is really quite warm. It gets very, very cold as it approaches the mesosphere. The mesosphere is cold, gets a little warmer. Stratosphere starts out warm, gets a little colder, and then we get to the troposphere. You need to know the troposphere and the stratosphere, at least because there's a lot of talk in the media about what these mean in terms of climate heating. But people are always talking about, oh, the troposphere hasn't heated up enough. One thing to keep in mind, you guys know this from physics, is that gases heat up slower than solids, and we should leave water out of it, than liquids, partly because their particles are farther apart. So the more you heat them up, the more they move apart, and they just transfer all the kinetic energy. So, some of that we got to keep in mind. The first stage of the climate system, because the climate system is started by its heat budget, which 99.9% of it comes from the sun. It's also the location of the greenhouse gases, which everybody freaks out about. We're going to talk about the greenhouse gases in greater detail, but these are the four that I really need you to know: water vapor, methane, carbon dioxide, and CFCs, chlorofluorocarbons. Those are the four bad guys, as we can call them, when it comes to atmospheric gases. And we really need to be careful with the bad guys label, or I should be careful. Without these things, life on this planet would not exist. So water vapor is vitally important. The greenhouse effect is vitally important. I like living in a temperate area, and we have the greenhouse effect to thank for that. The hydrosphere we've talked about quite a bit before. The hydrosphere are oceans, lakes, and rivers. The hydrosphere interacts with the cryosphere quite a bit, which is glaciers and sea ice. All of the cryosphere, that is glaciers and sea ice, is in the hydrosphere, as well as being in the cryosphere. There's a small amount of stuff in the cryosphere, like tundra, that isn't actually ocean, lakes, or rivers. But ironically, that also has a big issue with climate as well. Hydrosphere is important when we study climate. There's a reason why almost all climatologists are actually oceanographers by degree. It's because the hydrosphere has some of the biggest, arguably the biggest effect, even bigger than the atmosphere, on controlling terrestrial climate. We've talked in prior chapters, units, about the marine and continental effect, where you saw it today. It was like only about 60, 65 when you left school. By the time you got inland, it was probably 5 degrees warmer. That's part of the marine and continental effect. The ocean absorbs a lot of heat. Thanks, ocean. And then the continent does not. Same thing with the evaporation precipitation latitudes, as you may or may not remember. Most of the energy at the planet is absorbed at the equator. It's transferred back to the atmosphere at higher latitudes through evaporation and comes back down to the surface through precipitation. And the ocean disproportionately stores heat compared to the rest of the land-based ecosystems, anything along the surface of the Earth. This graph is one right off of NOAA, and it's actually showing how much more energy since about 1980 that the ocean is storing all more and more. You've seen lots of graphs about sea surface, about temperature of the Earth, and people freaking out. And those are usually pretty... like gradual, like that. And they usually have a lot of variation. This one doesn't. The ocean's getting warmer, not a lot warmer, but it is getting warmer fairly steadily. And there's a lot to be said about what that could mean moving forward. The cryosphere is the frozen part of the Earth. I mentioned it already. It includes tundra. The words that I bolded and underlined are really, really important for this chapter. And one is albedo. Albedo is visualized in these pictures below. Albedo is a measure of how reflective a surface is. So alpha is sort of the generic, they show it right up here. The little alpha, the fishy alpha. Perfect reflection of light is 1.0. It looks like a 10, but that's not right. And like a mirror is almost 1.0, not quite. And it's important because the higher the albedo, the more that light is reflected as opposed to absorbed. This is really important because we know that there are these little mirror-like caps on either end of the pole, and if you notice over here, ice with snow has a very high albedo, alpha of 0.9, while open ocean has a much lower. This is not 0.6, children, it's 0.06. Water's a dark color. If you shine light on it, most of the energy will be absorbed as heat rather than reflected back as light. So albedo is really, really important. Besides albedo on the slide, we have positive and negative feedback loops. I'm going to take a few minutes here, so this will be a longer slide. Positive feedback loops are those that reinforce the original change. An example of a positive feedback loop could be seen here with the albedo. So as more and more heat is entering the atmosphere, warming the water wherever it comes from, more and more of the snowpack will begin to melt. So like over time, we would lose this snowpack. Eventually, we would have a lower albedo, which means that as the heat melts the ice, more and more heat is absorbed, which will cause more and more of the ice to melt, and that we would get a sort of runaway effect where as you add more heat is absorbed. So that's a positive feedback loop. An example of a negative feedback loop is a little more complicated. but we could talk about potentially, say, something like forest fires, where you have more heat or storms, and those generate more forest fires through lightning or just dry wood. When forest fires burn, they leave a lot of ash, and that ash is frequently kicked up into the atmosphere, which can cause less light to be absorbed in the area, and you get a negative feedback loop. We are going to spend a lot of time in class talking about positive and negative feedback loops. The geosphere and the biosphere are the last two, and I'll do these pretty quick. The geosphere refers to volcanic activity, anything really related to the Earth's surface. We'll talk about this a lot because this kind of gets a lot of traction in past climate changes, and we should talk about it here. It's in large part responsible for the mini ice age and whatnot. The geosphere also includes the crust of the Earth, and as such, it has huge amounts of carbon. So here's another word here that's underlined, is sequestered. Sequestered means that you take an element or a compound and it is locked away in a long-term scale of years, like millions of years. So the idea with carbon sequestering is, there's a bunch of different ones, but the one you're most probably familiar with is fossilized plants and like things like trilobites, with the little guys who crawled around the dinosaur age. When they died in very large amounts. They died faster than they could be decomposed. And because of that, they sort of were covered over with sediments and whatnot before they had fully broken down. When this happens, pressure and time turns their body into those lovely fossil fuels that you and I both use every day when we go to school. So that's an example of a sequestered substance, sequestered carbon, is that normally this would be locked away for millions of years and only come up through volcanism. Other terms, and we're going to spend a decent amount of time on the biosphere, but just an overview for now. There's a lot of talk about proxies. A proxy is any measure that is used as a stand-in for time. So, and frequently another variable. In this case, it'll be temperature. You've probably heard of using tree rings to look at whether there was a drought or flood. You can actually tell temperature from that as well. Coral reefs are millions of years old, and they store isotopes, which are present in different amounts depending on the temperature of the atmosphere. Same thing with fossils, particularly fossilized pollen. Takes up carbon-14 at different amounts based on temperature. So there are many biological proxies. When we do our modeling lab, some of them will be taken into account, but you should know that word since we talk about it. Another word, I guess I'm just going to make you look it up, is paleoclimatology. It's basically the study of early climates. Paleoclimatologist, that horrible movie we're watching, Dennis Quaid is a paleoclimatologist. And in terms of the biosphere, some species sequester carbon on global scales. We'll talk about this in greater detail when we get to the iron hypothesis. But what this generally refers to is that, primary producers in the ocean, the little tiniest organisms, can take away and sequester more carbon than anything else on the planet. And finally, when we get into the possible solutions for the current climate shift, we'll talk about the high nutrient, low chlorophyll zones in the equatorial Pacific and Antarctica. There's a lot of experiments that are being done with them right now. And we're going to stop right there for this video.